Hello everyone. In this video, I'll be talking about Lanchester's war model, which was designed by the British engineer and RAF pilot Frederick William Lanchester during World War I. So he proposed a combat model to predict the outcome of a war using differential equations. And how he did that, we'll be learning in this video. So before that, there are two variations of this model. So, first one is called the conventional aimed fire model. The second one is the unaimed fire model. In the conventional aimed fire model, a shooter is directly targeting an enemy. So let me explain this better with the help of a diagram. Suppose we have two armies, a green army and a yellow army. So in this model, when this shooter will kill this one, afterwards he will move on to the next enemy and then to the next and so on. Similarly, the other soldiers will target one enemy. After killing an enemy, they will move on to the next and so on. So, as the enemies are destroyed, the firepower of the shooters become more and more concentrated on the remaining targets. So, this combat model is given by Lanchester's square law, which we'll be discussing in this video. In the unaimed fire model, which is the exact opposite of the conventional one, a shooter fires upon an area in which the enemy is presumed to be. So let me explain this again. Here we have the green army and the yellow army. So this shooter will concentrate his fire power on a specific area. So even if the enemy is destroyed, the shooter continues to shoot this area as a whole and his firepower remains concentrated in this area. Similarly, the other shooter will concentrate on some other area and so on. So this model is given by Lanchester's linear law. So now let's look at what the conventional model is. So imagine there are two armies. Capital P and capital Q. So let the number of troops or soldiers of capital P army be small p and the number of troops of capital Q army be small q. So the differential equations will be P dash, this is small p, which is a function of time, is equal to minus alpha q t. So what this means is that the decrease, the minus sign over here indicates decrease in the number of soldiers of P army is equal to alpha times the number of soldiers of Q army. So, and this alpha is called the lethality coefficient or the fighting effectiveness of the Q army. So similarly, for the Q army, we'll have the equation as Q dash T is equal to minus beta P T. Over here, beta is the lethality coefficient of P army. Okay, so what it essentially says is, if that the number of soldiers of Q army will decrease, the rate of decrease of number of soldiers of Q army will be equal to the product of the lethality factor of P army and the number of soldiers of P army, which kind of makes an intuitive sense of what we are talking about. So now let me write these equations properly again. dp by dt is equal to minus alpha q, this p1 and dq by dt is equal to minus beta p, this p2. So now dividing 2 by 1, we get dq by weight, dq by dt upon dp by dt is equal to minus beta p upon minus alpha q is equal to, so like, which will be equivalent to dq by dp is equal to beta p and alpha q. The minus signs will cancel out. So I'll rewrite the equations. dq by dp is equal to beta p upon alpha q. Then transposing, what we get is alpha q dq is equal to beta p dp. Now we integrate both sides. So what we get is alpha q dq is equal to beta p dp. So alpha q square upon 2 is equal to beta p square by 2 plus c, which is an integral constant. So alpha q square minus beta p square is equal to constant. Now this is a very, very important equation. So what this essentially tells us is that the fighting effectiveness of an army, for example, the Q army, the fighting effectiveness of the Q army is given by alpha Q square, and the fighting effectiveness of P army is given by beta P square. So we see that this fighting effectiveness, let the fighting effectiveness be a variable f. So it is proportional to the square of number of troops of an army, and proportional to the lethality factor of an army. So the conclusion that we draw from this equation is that the outcome, rather than that, the fighting effectiveness depends more on the number of troops in an army, more than the lethality factor. So let's solve an example using this model. So we have a sum over here. P dash is equal to minus 4q and q dash is equal to minus p. And the initial conditions are P of 0 is equal to 1500, which means that the number of soldiers at time t is equal to 0 are 1500, and in the Q army the number of soldiers are 900. So what we have to find out is who wins in what time and what are the losses. So let's see. So let's look at the first equation first. So if we differentiate the first equation, what we get is P double dash is equal to minus 4 Q dash, which will be equation 3. Now putting equation 2 in 3, equation 2 in 3, we get P double dash is equal to minus 4 into minus P is equal to 4P. Then we solve it using second order differential equations, and after we solve it, we get P is equal to C1 e raised to 2t plus C2 e raised to minus 2t. Now first of all, P of 0 we are given as 1500. We have to find the values of C1 and C2 so that we get a valid equation for P. So to find that, we are given P0 as 1500 and P dash of 0, which we'll be deriving from this equation over here, will be minus 4 into Q, and Q we are given as 900, so which will be minus 3600, and this equation P dash will be equal to 2c1 e raised to 2t minus 2c2 e raised to minus 2t. So let me write both the equations properly, and we'll solve for c1 and c2. So p of 0 is equal to c1 e raised to 2 into 0 plus c2 e raised to minus 2 into 0, which will give us 1500 is equal to c1 plus c2, which is our equation 1. Similarly, p dash of 0 is equal to 2c1 e raised to 2 into 0 minus 2c2 e raised to minus 2 into 0, which will be minus 3600, which we derived over here, is equal to 2c1 minus 2c2, or we can write it properly as c1 minus c2 is equal to minus 1800, which is the second equation. Solving for both, we get c1 is equal to minus 150 and c2 is equal to 1650. So the equation for p, we can rewrite it as p is equal to minus 150 e raised to 2t, and wait, let me write it properly, e raised to 2t plus 1650 e raised to minus 2t. So now let us solve for q. Let us derive the same equation as we did for p. Now we'll derive it for q. So again we have q dash is equal to minus p. So q double dash will be minus p dash, be equation 4. So over here we'll be substituting this equation, p dash is equal to minus 4q. This equation we'll substitute here. So substituting p dash is equal to minus 4q in 4, we get q dash is equal to minus of minus 4q, which is equal to 4q. So q dash is equal to 4q, q double dash minus 4q is equal to 0. So again when we solve this, we get an equation as q is equal to d1 e raised to 2t plus d2 e raised to minus 2t. Again we solve this for d1 and d2, and our initial conditions are q of 0 is equal to 900 and q dash of 0, which is minus p, which will be minus 1500, because initially we were given q dash is equal to minus p. So according to that we have q dash of 0 is equal to minus 1500. So applying these conditions, we'll rewrite the equations as q of 0 is equal to d1 e raised to 2 into 0 plus d2 e into minus 2 into 0, which will be 900 is equal to d1 plus d2. This is our first equation. And similarly for q dash, the equation will be 2d1 e raised to 2t minus 2d2 e raised to minus 2t. So for q dash of 0, we get 2d1 e raised to 2 into 0 minus 2d2 e raised to minus 2 into 0, which will be minus 1500 is equal to 2d1 minus 2d2. So writing it properly, d1 minus d2 is equal to minus 750. This is equation 2. So when we solve 1 and 2, this equation and this equation, we get d1 is equal to 75 and d2 is 825. So we rewrite q equation as q is equal to 75 e raised to 2t plus 825 e raised to minus 2t, and p, which we had derived earlier, was minus 150 e raised to 2t plus 1650 e raised to minus 2t. Now we'll graph both the functions, and what we get is, this is the graph for Q army and this is the graph for P army. And we see that when we graph the functions, the value of Q will never touch 0, while the value of P will touch 0 at some value of T. This means that the Q army will never be fully decimated, but the P army after certain time T will be completely eliminated. So Q army is the winner in this case. Now we will have to calculate the time in which the P army is defeated and the losses sustained by both the sides. So write P equation again. P is equal to minus 150 e raised to 2t t plus 1650 e raised to minus 2t, and we'll set P is equal to 0. Now why we are setting P is equal to 0? To find time T in which all the soldiers of the P army are killed. So when we set this to 0, 0 is equal to minus 150 e raised to 2t plus 1650 e raised to minus 2t. So e raised to 4t is equal to 1650 upon 150, which will be 11. So e raised to 4t is equal to 11, and t will be ln 11 upon 4, which is roughly equal to 0.6. So what we are saying here is that in 0.6 seconds the P army will be completely defeated by the Q army. Now we find the losses sustained by the Q army. Let me write it. Loss sustained by the Q army at 0.6 seconds. So that is very simple. What we have to do is, this is the equation we had for Q army, e raised to 2t plus 825 e raised to minus 2t. We simply substitute t is equal to 0.6 in these equations, and we find the value of Q. So Q will approximately be 497.49, which is, obviously we can't have people in fractions, so we'll round that off to 498. So 498 is the number of soldiers killed in the battle. So the losses are 498 and survivors of Q army are 900 minus 498, which is 402. So this is Lanchester's square law. This is how we understand the dynamics of a battlefield using a simple system of differential equations. Now, one more beautiful feature of this Lanchester war model is that we can even include other factors and more number of armies in the equation. For example, this was the equation that we started with, x dash is equal to minus ay, and we can also include other factors and more number of armies in the equation. For example, we can write x dash is equal to minus ay plus r of t, where r is the rate of increase of number of troops. And we can also write minus c x, where c is rate of decrease of soldiers, notice the minus sign over here, since the soldiers are decreasing, and over here there's a plus sign because the soldiers are increasing. So this decrease can be due to any reason. It can be due to diseases or anything. So that is something that we are accounting for, an unpredictability factor. So this, and we can also have x, y and z armies, 3 armies in the equation. So this was Lanchester's war model. I hope you found it informative. Thank you.